when the bell rung, Cole made a prediction. He made a prediction. And I think he used some probability to do it. I'm not sure if he thought about the probability or not. There probably wasn't any calculation. But Cole's prediction was something about the amount of students here. It was about the amount of students coming and the amount of students coming when they came. He thought probably some of the class would be late. Now, he was pretty safe in betting that because the bell had already rung. We thought that maybe sharing our duties in every Soviet student paper might help you as you came in. On which number 2 says to be diligent in study and punctual attendance, never being late to class. Oh, sorry, I got lost here. I know some of you had a reason why. But actually, I was mostly just talking about Cole's prediction because it was a perfect segue into this lesson. So, this is actually, I think, a fairly useful lesson. Not that in life you're always actually using numbers, but I would say one of the most impactful podcasts I listened to in the last probably 5 years was on one of my favorite podcast series. It's called The Art of Manliness, kind of a weird name. But he basically interviews a bunch of people. But he interviewed someone, it was probably like 5 or 6 years ago, about using probability to kind of think about decisions. And this interview was with a former poker player, and she was talking about thinking of life in terms of bets. And her idea was that usually decisions you make can be kind of thought of, in hindsight as either successful or not, just based on outcome. But that's not usually actually sort of fair to yourself. You can't know the outcome before you make the decision. But you can know, was it a good decision based on the information I had then? And this is sort of a part of that, mathematics. Yeah.
Is it a good math thing that we play poker?
Well, we can talk about that later. There's lots of probability in there. And Malak's going to bankroll all of us. Because the second that I encourage a gambling game in school, I'll probably lose my entire teaching, career.
Then you have to think about your career.
But I do like poker very much. It's a great game for thinking of probability. Because there's a lot of decision making in that Malak that's related to this. Like, what kind of thing is a reasonable decision based on the information I have, and what isn't, right? When you just have 2 cards in front of you, you're dealing with all of these possibilities that could happen in the hand with what other people have. This is going to go a little bit of a sidetrack, but you asked, so I'll just talk about it for a second. So let's say I'm sitting on, does anyone know how to play poker? Or like Texas Hold'em poker is kind of the more famous version. So let's say at this point in the game, all 5 cards have been put out there. Let's say there's an ace of clubs, there's 2 of hearts, there's 7 of diamonds, there's 8 of clubs. No, actually I'm going to say 8 of diamonds.
No.
And there's 6 of, let's say, diamonds.
Holy fuck.
Okay, so there's some possibilities available, hey? Actually, and maybe let's even say this 2 is of diamonds, just to make this even a more, thought-provoking situation. And let's say I'm sitting on an ace of hearts and an ace of spades. Pocket aces. So, shockingly great hand, right? Awesome hand. And the flop gave me ace 2-7. I'm sitting there, okay, I'm sitting on 3 of a kind in aces, betting everything I have. Malak's giving me her money, this is awesome. Someone for some reason has stayed in, and they were sitting on just like a 4 of diamonds and whatever, 7 of clubs or something like that. Currently, they are beating me. They have a flush in there. Right? They have five diamonds available. The kind of decision making that we're kind of talking about that happens in poker is what kind of thing can you know at certain points. So at a certain point, probably when you only knew this, the person who was sitting on a 4 and 7 should have folded.
Yeah.
But they ended up getting 2 more diamonds. They ended up having their flush and diamonds. My ace and ace, which looked really overpowering initially, became a lot less powerful. And that's all that I'm trying to say is, in this case, the information you're dealing with that makes you make decisions in poker is actually very mathematical and really causes you to think through. The strongest poker players actually know exactly the probability of everything coming up at each play. And generally, in a situation like this, let's say you're the person sitting on the 4 of whatever it was, diamonds. but they should be thinking before they go crazy on betting is what hands can beat me, right? What things are possible that could beat me? Well, the answer in that case is any higher diamond could beat that person also. Well, there's actually also straight flush available. If someone had the 9 of diamonds and the 5 of diamonds, or the 9 and 10 of diamonds, they'd have a straight flush, which is the second best possible hand in the game, which you never see. So there's a lot of things available that could beat the 4. The whole point is you're kind of thinking in that game of how do the probabilities of what could happen inform my decision and what's a reasonable bet to make at the time. Okay, so outside of that extremely complicated probability game, which is quite fun, but as I mentioned in all of these things with the gambling kind of examples, so the probability that's always gets brought up, you need to be really careful. You need to be really careful, right? Lots of people get into significant trouble with gambling, and my both personal and teacher advice is that this should never be something done with any real money. People will play poker with either $10 or $20 buy-in with their friends. That's a different thing. But if you're talking about going into the casino and spending money, just be aware you can really dramatically change your life in a really bad way quickly. You know, things like this. I speak partially from for working at a school, and I used to be on our community board. We would do lots of casino fundraisers where you go in and you are the banker for the night, or you go in and you help with something.
There's a reason you do it, because you win.
You always win. In fact, one night you didn't. Somehow the house was dead. I thought, wow, that's really surprising. But what they do is they take an average of the 3 months and they pay out every fundraiser at that average rate. So that night we lost. The house lost. It was so unusual. Guess what we still made for those 3 days? We had $100,000 for the charity over the 3 days. So though that day we were down, over time they were averaging $35,000 a day. Coming into that casino. That's a remarkable profit, eh? And I'll tell you, there were a few people who would come up to the spot where I was a cashier to get new chips, and they came in 3 times. But one guy was one of the more depressing ones I've ever seen was he came up to me 3 different times to get chips, and each time you could almost just maybe I was reading into him, maybe this is actually what he was feeling like, but it looked like kind of like lower and kind of don't even look at me, give me more chips, let me go and wreck my life more. So yeah, pretty sad. So it's certainly one where just recognize the house is really profitable.
There's a reason there's so many casinos.
Reason there's so many casinos, reason they're so big and flashy, why they offer so many free food, free drinks, those kinds of things. Or not free food, cheap food. Yeah. Okay, total side note, maybe we'll do some math now. Good job derailing me, Malak was very good at that. Her hope is to get me one day to talk 80 minutes about random things that are not the math. It'll probably work sometime. Fortunately, we have a nice short lesson today, so it wasn't such a big deal. Okay, so let's think about this example. It's, I think, quite a simple one, actually. Bert wants to know, out of 2,000 people, Bert, who likes Pepsi, who likes Coke? So instead of asking all 2,000, he asks a sample of 30. Out of the sample, 15 like Pepsi, 15 like Coke. Now you can argue whether this is an appropriate sample. I think this is too small of a sample. For this, it's likely with that small of a sample to have a significant bias or a significant skew in some way. But whatever, we're using this sample of 30 to figure out what's probable about the whole 2,000. What conclusion can Bert make about the 2,000 based on the sample? Yeah? So,
half of people like Pepsi, half of people like
that's great. That's exactly right. That's what it tells us. But let's actually even go one step further. What does it tell us then about the sample of 2,000? How many would you expect out of the sample?
1,000.
Right. So I would say approximately 1,000 will like Coke. 1,000. Who's taken science 30 or chem 20 or physics 30, any of those? When you're measuring data in an experiment and you find, let's say, 10 points, in the higher level sciences, you're generally not able to just put your dots. Usually you put in dots with either circles around them, and maybe depending on your error range, you may even have error bars, which basically says, based on the error in my calculation, it's probably somewhere, or it's certainly somewhere between here and here. This is where I think it is, but it's certainly somewhere in this section, right? That's how you account for error in science. with probability, we need to kind of think similarly. We don't write it. But the reason why I said approximately is that I recognize that there is some error. It's actually very unlikely that exactly 1,000 will like Coke and 1,000 will like Pepsi. I don't know if it's like a range of 900 to 1,100 or something like that, but I know that somewhere in the range of 1,000 and 1,000 is what this tells me. Silver pointed out that 50% go each way, but probably not exactly. Probably not exactly. Probably something around. Okay. So the conclusion is that somewhere in the range of half and half seems to be the split. By the way, how does this compare to what your anecdotal evidence means? Do you think that they're about 50-50, or do people like one more than the other?
I think people are gonna like Coke more.
My observation is also that Coke is more popular. It's funny when you're at a restaurant. I try not to drink pop. I have a really bad sweet tooth. I like to hoover up any sweets that are on me, so I don't drink pop to kind of partially make up for that. But we go to a restaurant and someone will ask. They'll say, "Oh, do you want a drink?" And someone will say, "Do you have Coke?" And they'll say, "No, we only have Pepsi." "Oh, okay, I'll have coffee instead." I'm like, "What? Really? So similar." But people have strong preferences, right? I always wonder about blind taste tests if you could actually tell. But I think Pepsi is a little sweeter, of course. A little sweeter, a little syrupier.
Right, you can blind taste this.
By the way, let's see that in this class. Coke? Coke?
Oh, Coke.
Who likes Coke?
I don't really care on this.
We'll
Okay,
figure it out.
Pepsi?
Oh, Pepsi.
Okay, and no preference. Okay, but it was slight Coke. It looked like it was 5 to 3 to 5 or so. Okay, how about this? Sample of 5,000 how many write with their left hand? So 5,000 people, how many of them would you expect to write with their left hand? And I think what we should say here, what conclusion is, what would you expect? Right? It's not what exactly will the number be, but it's what would you expect. This is like yesterday when we were playing those dice games. It didn't always go exactly as we would expect. But like in that last game where basically we had a fairly significant skew toward partner A, well, partner A didn't always win. I think in the class, 6 of the groups partner A won and 2 of them ended up being a tie. But still, we expect partner A to win. We know that the odds are in partner A's favor, even though sometimes in that small example it may not exactly work that way. Okay, so in this one, asked a sample of 50 people and found that 5 of them write with their left hand. 5 of them write with their left hand. So what would you expect then about the group of 5,000? Well, in the sample, 5 left hands out of 50 total. So the rate is, what's the rate? What's 5 out of 50? That look great? 1 out of 10 is 0.1, which is, by the way, approximately the average. It's about 10% is what it is. Although a really disproportionately high number of U.S. presidents are left-handed, which is kind of funny. Something like 50% of presidents have been left-handed, or some crazy number like that. My wife is like left-handed. She likes to point out to me how all these successful people are left-handed.
My brother's left-handed.
Yeah, no one cares. But sorry, not to you, but that's how I feel. But actually, it would be worth thinking. I wonder why that happens statistically. Like, sometimes these are correlations, sometimes they're causation. I actually kind of wonder if, because the world is slightly set up to be favorable to right-handed people, I've wondered if, just having a slight bit of resistance, having to problem solve dealing with right-handed stuff in your life maybe makes you slightly more likely to...
you like both hands?
Pardon me?
What if like both hands?
Then you're ambidextrous and you're amazing.
Yeah, I didn't feel like that.
Okay.
What if, in the past you left
You're
people were,
amazing.
Discipline or be left-handed? What if all right-handed were disciplined?
Yeah, good question. We would have a lot of people being disciplined, that's for sure. Yeah, discipline was different in school. Sometimes I'd like to bring this back. My dad used to get the strap every day, he said. But the reason why he used to get the strap so regularly is that my dad was a smoker in high school who was trying to quit smoking and use spits to, quit smoking. But his one teacher really hated him using spits, so she just done the strap every day because he was chewing spits in school. I thought that's a little unreasonable, but whatever. Okay, let's go back to math. Sorry, I'm really off the left. Okay, 0.1. All right, and we're wondering about out of 5,000. So how can we figure this out? What's 0.1 of 5,000?
1,000?
500.
Oh, right, yeah. Are you sure?
Yeah.
Like 500.
Yeah, right. And if we think about this, all you're going to do is take this ratio and multiply it by the 5,000. You could say, 1 out of 10 times 5,000, or you can say 0.1 times 5,000. But yes, we find out that we expect, and I'm going to say approximately 500 people to approximately equal to somebody's.
And then tilde.
Or you'll sometimes see this instead. Same thing.
So,
Now, this is just what we've done. What I'll show you though is the way you find the predicted number, this is what we just did, is by multiplying by whatever your experimental probability was. That's what we found is the 0.1, and then times the size of the population. Bye-bye, binder. Yeah, just throw the actual binder in the garbage and the rest of your paper a second. Okay, so broken light bulbs. Feldman Specs 25 finds 2 broken ones. Okay, so first of all, how many are in the population? 10,000, we're told them. How many are in the sample? 25 were in the sample. She inspected 25. What's the experimental probability of a light bulb being broken? Well, it told us 2 out of those 25 were broken, 2 of that sample. And we could call that 8% or 0.08. As I've mentioned here, I don't care the slightest bit whether you use a fraction, a percent, or a decimal in your multiplication. They're all the same thing that matters. However, most people make the least mistakes in math if they use the decimal. They're all the same, but the least mistakes happen when people use decimal. So that's what I'll show. Okay. Being candid, I always use a fraction. I like working with fractions. That's what I use most often. But I found that students make mistakes the least often with the zero or with the fraction, or with the decimal. So that's what that's just. Okay, so in the group of 10,000, what would you expect? Well, take that 0.08. That's your experimental probability, and multiply it by the size of the sample. That, and you get good 800 broken bulbs. 800% would be a very different answer. 800% of 10,000 would be 80,000 broken bulbs out of those 10,000 broken bulbs, which doesn't make a ton of sense. Or something. So 800 of the 10,000. Okay, car accidents. High school students, car accidents. I wonder if high school students have car accidents at a higher rate than the average driver.
Probably, I don't, yeah.
Cole, what do you pay for insurance?
Just for just me?
Yeah,
I pay $250. It's a bit low.
$250 a month.
Yeah.
That.
I know my friend pays $500 because he's gotten into like so many crashes. Like,
Wait, but sorry, let's just do this for a second. So 250 times 12, that's $3,000 a year.
Yeah.
Approximately is what Cole pays. Guess what the average 30-year-old driver pays with no history of crashes?
So cheap.
Yeah, something like $1,000 a year. So what does the insurance company think about 18-year-old driver versus 30-year-old driver?
I'm 17, so even worse.
Yeah, they think you're a big menace and a big threat,
And I
right? And in truth, if you show even as low as 5 years of good driving, your insurance drops like crazy. But they think that the rate for high school students is way higher because especially high school men have really, really high rates of accidents and all that. Hi. Okay, so let's do the same thing here with this car accidents. So at Center High, 30 students are being surveyed about car accidents. Now, population is the whole group. That's this whole thing, 2,500 students. The sample is how many were asked. That's 30. This is probably, if you're going to make a mistake here, this is probably the mistake is which one's the sample, which one is the population. What's the experimental probability of a student having had an accident? Well, the sample was out of 30. And how many had an accident? Well, 40. 4 out of 30 have had an accident. So that ends up being like 0.13 repeating, or 13.3%. Feel free to check my math. That's really hard to do. Now, it's not saying like horrible accident, but it's saying some kind of accident. So then, how many did you expect? Now, as I'm thinking this, I start having those questions. I wonder if that is an unusually high sample. Now, the problem isn't really leaving us space for that, but I still think to be a good mathematician, you have to ask questions at every spot. And I'm kind of wondering, well, based on what I've seen, I wonder if this is like a representative sample or not, right? I wonder if this represents the average or not. Well, last year, for our rugby team, we had a student driving some other students to a game who crashed on the drive. So that was certainly one tick against letting students drive other students. But I wonder. I don't know if this would be a higher or lower percentage. I kind of think probably higher than average. But still, we're using this as our experimental probability here. So 0.133, whatever repeating, times our population size, 2,500. This should give us our expected number. So I'm going 4 out of 30 times 2,500. And I get that I expect 333.3333. So I should expect 333 students and a third of a student get scratched. Okay, what should I say then? What should I say?
30.
Oh, rounded. Okay, good idea. So we'll say approximately 333 students. Okay, I just wrote this down, but I want you to think about this for a second. I said approximately 333 collisions, but I think that's a little imprecise. Well, let's just think about what was asked. What was asked was how many students have been in a car accident. Is students who've been in a car accident possibly a different number than the amount of collisions?
Yeah.
Possible that Cole was driving me and Adam and and Matthew all to school, and he blindsided into some other truck. Well, we would all say we've been in a crash, but actually there was only one collision there. So I think what I've said here is slightly inaccurate. I'm just saying that to kind of show sometimes the wording actually does matter there. So we say approximately 333 students have had an accident. Now, being frank, would I actually dock a mark for that? Of course I wouldn't. But it's not saying the same thing. This is more precise. Yeah. There was a name Isabel up here.
Yeah, but I didn't have my water bottle.
True. It's costly. Actually, I was going to ask that, but then I realized it's still water in it.
I can feel it still.
Okay, fine, thanks. Okay, now these cats. Some cats have more than the usual 18 toes. Wait, what? More than the usual 18 toes. Wait, 18? Oh, so I'm learning something new here. 5 on the front paws, 4 on the back toes. Huh, interesting, slightly different. So some have more than usual. These are called polydactyl cats. Do you want to predict how many there be? Oh, hello, sir.
Hello.
Wait, didn't you tell me King Ennis?
What?
King Ennis? You
Yeah.
just call him Mr. It's King Ennis, Your Highness. Sir. Yeah, there we go.
I'll even accept your honor. Now, can I see you just for a second? Just 2 seconds?
You can be at 5.
Yeah.
Get out of here. Okay, so
Look at that.
she's going to miss part of our lesson about polydactyl cats. I'm sure she's so sad. So she found that out of the 75 cats she sampled, and I don't really want to know actually how she sampled it. It might have been a little bit messy, but she was checking 75 cats, their toes. That was quite a job. She found that 3. So First of all, sample was 75. 3 of the 75 were polydactyl. Okay, and population has 1,500. Oh, okay, that was very prompt. There we go. Yeah, there we go. No, we're on back to the probability. Okay. So, I'm going to do something here. I told you we can do this as a fraction or a decimal or whatever, so this time I'm just doing it as a fraction like I would. So my experimental probability, 3 out of 75, times my sample of 1,500. I expect 60, or we would say 60 POLYVACTYL cats. Nothing means with pterodactyl cats.
It'd be crazy.
That would be quite the interesting breeding experiment.
That's the Jurassic Park we need to see.
That would be something. Those of you that have taken high-level biology, make it happen.
Do it in your backyard.
Now drop the star, guys. Okay.
I sort of think today's is going to take you about this long. Take a look.
Yeah, that was
Oh, ready?
That
Bruh.
was big.
What do you use the voice? Hang the rest.
Yeah, finish your work.
So, we go
Echo the drainage